In this video, we'll be discussing the idea of formal charge as how it's related to deciding which of several possible Lewis dot structures are the most reasonable. In the previous example, there were two possible ways we could have formed the multiple bond. We chose to form the multiple bond using the oxygen lone pairs where the oxygen was not bonded to the hydrogen. But we could have also used a pair of electrons from the oxygen that had the hydrogen attached to it, and we need to decide which one of those is better. This really comes down to a discussion of what we refer to as formal charge. And formal charge is kind of a bookkeeping approach. It makes an assumption that the atoms possess electrons, which is not really true, but it is going to keep track of the overall distribution of the electrons and the amount of charge associated with drawing various Lewis dot structures. So, to determine a formal charge, we are going to assume that half of the electrons in a bonding pair belong to a particular atom. They start out from some atom. Lone pairs are assumed to completely be owned by a particular atom, so they both belong to the atom. So, here's the basic formula for calculating the so-called formal charge. If you have a particular Lewis dot structure, you can first determine the number of valence electrons for a particular atom. This is done in the normal way by drawing out the Lewis dot structure, or the electron configuration for that atom. And then we're going to subtract away half of the bonding electrons that are essentially half of the shared pairs of electrons. And then in addition to subtract away those electrons, we're going to subtract away all of the lone pair electrons. If this then is performed, the resulting positive or possibly negative values are going to tell us something about the so-called formal charge. In the case of a polyatomic ion, the sum of all the formal charges has to add up to the overall charge of that particular ion. Shown here are some guidelines for determining which of a number of possible Lewis dot structures might be the best description for that particular molecule. The first general rule is that the best Lewis dot structure will have the lowest possible formal charges for all the atoms involved. So in other words, if you have a molecule where all the formal charges are 0, that's probably better than a situation where one or two of them have some other formal charge value. So this then also is true for some polyatomic ions where the formal charges of atoms may all be 0 except for 1 or possibly 2. The overall charge of the polyatomic ion has to be the same as the sum of the formal charges for any individual atoms. The second rule here is if a Lewis dot structure has atom with non-zero formal charges, then we want a structure that has the fewest atoms with formal charges, and again they must add up to the overall charge. So if the molecule has a net charge of 0, and you end up with Lewis dot structures where one atom is got a formal charge of +1 and a different atom is -1, that would be a less useful Lewis dot structure than if you could draw a structure where all the atoms have 0 formal charge. And so a Lewis dot structure with atoms having opposite charges Usually those are atoms close to one another. If that is possible, that would be preferred over having them highly separated. And then finally, when you have more than one possible Lewis dot structure, the negative formal charges should end up on the more electronegative atoms, and any positive formal charges should be on the least electronegative atoms. As an example of how to use formal charges to determine which of several possible Lewis dot structures that is going to represent the best description of bonding, we're going to consider carbon dioxide. If we look at the three possible Lewis dot structures shown here, each of these is possible in terms of satisfying the octet, but we need to examine the formal charges for each of the atoms in the structures and see which one produces the least amount of formal charge. In our formula for calculating formal charge, again, we need to know the number of valence electrons for a particular atom. We're going to subtract away half of the bonding electrons for that atom, and then subtract away the number of lone pair electrons for that atom. Okay, to determine the number of valence electrons for each of the atoms involved, each oxygen has 6 valence electrons. The carbons have 4 valence electrons. So we can determine our formal charges. In the case of the oxygen, which is on the left of the first structure, the total number of valence electrons is 6. We have 3 bonds between that oxygen and carbon, so half of the 6 electrons in these bonds is 3. And then finally, there's 1 lone pair of electrons on that oxygen, so we're going to subtract those away as well for a total of +1 formal charge. In the case of the central carbon atom, there are 4 valence electrons, there are 8 bonds, so we're going to have half of those electrons, or excuse me, there are 8 electrons and half of them are going to be subtracted away. There are no lone pairs on the central atom, so the formal charge of carbon is 0. In the case of the final remaining oxygen atom on the right-hand side of that structure, there are 6 valence electrons. There's a single bond with 2 electrons. Half of 2 is 1. And there are 3 lone pairs, or a total of 6 electrons that are in lone pairs. This gives a formal charge of -1. Now, if we consider the central atom, or the central structure, in this case, again, oxygen has 6 valence electrons. The oxygen in this case are the same, so we're going to subtract away half of the 4 electrons that are shared, and then there are 2 lone pairs, so we're going to subtract away those 4 electrons for a formal charge of 0. In the case of the carbon has 4 valence electrons, and we're going to subtract away half of the 8 bonding electrons. The carbon has also 0 formal charge. Now, considering the structure on the right, the oxygen that is furthest to the left has 0 formal charge, just as we calculated previously, since there's a double bond and 2 lone pairs. The oxygen that's in the middle, in this case, has 6 valence electrons, but there are 4 bonds, so a total of 8 bonding pairs or 8 shared electrons. Half of 8 is 4. This gives a formal charge to that oxygen of 2+. This is not a particularly good situation for a very electronegative atom such as oxygen. Finally, the carbon on the right normally has 4 valence electrons. We subtract away half of the bonding electrons, and then we have a total of 4 lone pairs on that carbon. This gives a formal charge of 2 minus to the carbon atom. This structure is not particularly good because the more electronegative formal charge is not going to the most electronegative atoms, and so this is not a particularly good structure. The problem with that structure on the right is that when we drew the skeleton structure for that, we didn't put the more electronegative atoms, the oxygen atoms, on the end and put the carbon as the central atom. So this is not a good structure at all. So hence we go back to the central structure, and this has the lowest overall formal charges for all the atoms. This is the most probable structure and the best description of the book. Shown here is another example of using formal charges to help determine what's the best possible Lewis-Dot structure. We have the N2O molecule, sometimes known as nitrous oxide. Again, the formal charges are determined by taking the number of valence electrons and subtracting away half of the bonding electrons and all of the lone pair electrons. The first Lewis-Dot structure shown here is a situation that has a triple bond between the two nitrogens and a double bond between the central nitrogen and the oxygen. The problem with this structure is the violation of the octet rule for the central atom. In the case of the second structure, we now have double bonds between the central nitrogen atom and the two terminal atoms. This does not violate the octet rule for any of the atoms. And then finally, we have a structure where we place the oxygen in the center of the atom, or of the molecule, double bonds to the terminal nitrogen atoms. This is not desirable in terms of putting the more electronegative atom as a terminal atom. The number of valence electrons are shown here. If we go through and calculate our formal charges for the structure on the left, while this does produce formal charges of 0 for all the atoms, again the problem is the violation of the octet for the central atom. For the second structure, we end up having formal charges on both of the nitrogens, +1 for the central atom and -1 for the terminal nitrogen. This is not as good as if we could find a structure where all the formal charges are 0, but our final Lewis-Dot structure has formal charges where oxygen becomes +2 in terms of its formal charge, and that certainly is not very desirable in terms of a very electronegative atom. And so overall, each of the atoms has some sort of formal charge, not as desirable as the central atom, which has only 2 atoms with formal charges. The other thing that makes this a little bit better is that we have only 2 atoms that are sitting right next to one another, so that's probably the best of the possibilities here. So again, the first structure violates the octet. The third structure does not follow the rule about putting the more electronegative atoms as terminal atoms, so we come to the conclusion that the middle structure is the most probable description of the bonding.